Hello, and welcome to the session on Advanced TSQL with Microsoft SQL Server. I'm Christopher Richard, Managing Director and Chief Software Architect at G7CR Technologies India Private Limited. Pretty happy to take this session today on behalf of Microsoft, and we'll be trying to give you the most pleasant and enjoyable learning experience as possible. What we are trying to cover in this particular session would be topics like logical query processing. We'll talk about the differences between sets versus cursors. We'll discuss temporary tables. We'll discuss subqueries. We'll discuss some of the new analytical functions that's available. We'll talk in depth on joins and join strategies and the influences of indexes on these join strategies. We'll also discuss aggregation. Aggregation I'm going to leave out here. We'll definitely discuss pivoting data, and we'll talk about graphs, trees, and hierarchies, and how they actually work with SQL Server's new data type called the hierarchy ID. Now that's the objectives of the session, so sit back, relax, and hope you enjoy the rest of the session and the learning that's coming your way. Starting off with the logical query processing. Now, there are many unique aspects of SQL programming, such as thinking in sets, the logical processing order of query elements, and three-valued logic. Trying to program in SQL without this knowledge is a straight path to lengthy, poor performing code that is hard to maintain. So in this particular topic, of this session, I'm going to try and create some strong roots upon which you can actually build your Transact SQL programming knowledge, and this would most probably help you get thinking in the right direction. Now, thinking from the perspective of who are you submitting this code to in terms of Transact SQL, there is a component in SQL Server that is in charge of generating the actual work plan for a query, and this component is called the query optimizer. The optimizer determines in which order to assess the tables, which assess methods and indexes to use, which join algorithms to apply, and so on. The optimizer generates multiple valid execution plans and chooses the one with the lowest cost. The phases in logical processing of a query have a very specific order. On the other hand, the optimizer can often make shortcuts in the physical execution plan that it generates. Of course, it will make shortcuts only if the result set is guaranteed to be the correct one. In other words, what I'm trying to say, the same result set you would get by following the logical processing phases. For example, let's say to use an index, the optimizer can decide to apply a filter much sooner than dictated by logical processing. For this reason, it is important that I make it clear that you have a very good, clear, and thick distinction between logical and physical processing of a query. Let's discuss logical. Now, this slide and what we are trying to discuss now is the logical query processing. I'm trying to introduce you to the phases involved in the logical processing part. Like I said, not necessarily this will be the same when this is converted into a physical plan. Let me first describe each step that is there in this logical phase, and then we'll try and see if we can also do a small little demonstration where I walk you through these phases which you're looking at on the slide. Now, the slide has been there for maybe a minute or so. I'm hoping you've been able to run through it, and you can see it contains a general form of a query along with the step numbers assigned according to the order in which the different clauses are logically processed. The first noticeable aspect of SQL that is different than other programming languages is the order in which the code is processed. In most programming languages, the code is processed in the order in which it is written. In SQL, the first clause that is processed is the from clause. You can see there, I've got number 1 in the red there. So the first thing that he does is, the first clause that he processes is the from clause. While the select clause, which appears first, is processed almost last. You can see the select here is number 8 in the total of 11 steps that we actually have. So this is why you're most probably thinking in SQL is very different than thinking in all the other programming languages you work with. Now each step that gets executed here generates a virtual table that is used as the input to the next step. These virtual tables are not available to the caller, in other words the client application or an outer query. Only the table generated by the final step is returned to the application or the caller. If a certain clause is not specified in a query, the corresponding step is simply skipped and it simply goes on to the next one. Now the brief description of the logical query processing that you're looking at on the screen. Don't worry too much if the descriptions of the steps don't seem to make much sense for now. As we progress through the session and you look at some examples, you most probably will get better understanding of it. The first clause is the from clause. Now the from clause, a Cartesian product, that is a cross join, is performed between the first 2 tables in the from clause, if there were 2 tables. And as a result, a virtual table, let's call it VT1, virtual table 1, is generated. The next clause which you'll notice here would be the on clause. The on filter is applied on the virtual table 1, and only rows for which the join condition is true are inserted into virtual table 2. I hope you're able to imagine this flow right now. Look at the numbers on the screen. The from clause applies if there are more than 1 table there. It applies a cross join and gives you the Cartesian result of both the tables. And the Cartesian result of both these tables will be your virtual table 1. Then the second processing is the on clause. So he applies the on clause and picks up only the records that match the join condition, and he creates a second virtual table which will now store this particular result. Now you could have an outer join if an outer join is specified as opposed to a cross join or an inner join. Rows from the preserved table or tables for which a match was not found are added to the rows from the second virtual table as outer rows, generating virtual table 3. If more than 2 tables appear in the from clause, step 1 to step 3 are applied repeatedly between the results of the last join and the next table in the from clause until all tables are processed. Now I hope that you are really getting an imagination of your query right now going to the server. It picks up the first 2 tables if there were 2 tables. It creates a Cartesian results on that, applies the on condition now, and creates a second virtual table now which has the on clause. So first virtual table is a cross join, a Cartesian result. Second virtual table is after the join condition is matched. And if there was an outer join here, then a third virtual table will get created with the extra rows that are required from one of the tables. That will be a third virtual table that gets created. And if you had multiple tables in the from clause, in other words, you're creating a join on more than 2 tables, once it reaches the second or third table, virtual table, depending on whether you had an outer join or inner join. If you had an outer join, you'll have the third virtual table created. If you had an inner join, you'll have only the second virtual table created. This will then go ahead and again step 1, 2, and 3 will get processed, creating another virtual table. Now this will go on until all the tables in your from clause are completely processed. So that was step number 3. Now, after all the joins and the conditions are applied and you land up with your last virtual table, let's call this virtual table 3 in this scenario, it will then apply a filter, or let's call it virtual table 2. Let's assume we had only 2 tables for this sample in the from clause. So I apply the from clause. My first virtual table is the Cartesian result. I apply the on condition and I get my second virtual table, which is the one where the join condition already matches. Now after this, it will then apply the where filter, and it will create my third virtual table where only rows which meet the where condition is true are inserted into a fourth virtual table. We then have the group by clause. Now the fourth virtual table is picked up and arranged in groups based on the column list specified in the group by clause. You can see 5 here is the group by clause. If you had a cube or a roll-up operation, then this would be step number 6, where supergroups or groups of groups are added to the rows from the virtual table 5, generating your sixth virtual table 6. Now, once your cube and roll-up operators are basically applied and you get the virtual table 6, it will then apply the having clause. And the having filter is applied on the virtual table 6. And finally, only groups which have the having condition as true are inserted into a seventh virtual table called VT7. Now, after all this happens, it then assesses your select list. That is, the select list will pick up only the columns that you require and give you virtual table number 8. Now, once virtual table 8 is picked up, it will then do the 9th step, where it will do a distinct in case you have a distinct. That is the step number 9, creating another virtual table which has only distinct values. Finally, the system would run the order by clause in case you add an order by clause, leaving out only one thing. In case you had a top specification, that would be the last thing which would basically run before everything else runs. Now it's important to understand here the top specification. Once you do an order by, the order by does not return a set. So the order by returns a cursor. We'll be talking about cursors and sets in a little while from now. But if you're looking at this from the perspective of an angle, the order by clause is not a set based operation. So right up to step number 9, you were working with sets. In step number 10, the order by clause returns a cursor. It does not return a table. Now once the cursor is returned, the top clause will go to the cursor and pick up the specified number or the percentage of rows that is required from the beginning of the cursor and give you back the results to whoever basically called the application. So 10 does not result in a virtual table, it results in a cursor in case you have an order by clause in your query. And that's step number 10. And step number 11 works not on a set but on a cursor before returning it to a calling application in case you had a step number 11. If you didn't have a step number 11, then the cursor itself would be returned to the calling application if you had a order by clause. Now this, in simple, is the logical query processing. My strong recommendation for those of you who want to work with SQL in the long run, take a printout of this most probably, stick it on your desks, get familiar with it and start imagining your queries logical processing method while you're working with them, because it will give you, it will get you into the habit of writing proper code, because you will be able to visualize the flow of how your query is actually executed. So that was the logical query processing which was there. Now before we go ahead with anything else, let me just take you through one small little sample. I've typed the code in advance for most of the demos that we'll be doing, just to actually save time. So I'm going to take you through a small little sample here which will try and describe this. I'm going to go switch over to my virtual machine here. Most of our labs are done on virtual machines, and I'm going to open up a code here called the logical query processing. Now in this code here, in this sample query, I'm going to first run the code which is going to create 2 tables, the customers and the orders table, and then I'm going to populate it with some sample data so that we have something to actually work with. So I'm using my TempDB for this so that we can clean up easily. I'm creating a table called customers and I'm creating a table called orders. And then you can see I'm putting in some data values into those tables, and then I'm going to do two selects from it so that you can see that that was successful. So that's the first step. We've got a couple of records. We've got around 4 records in the customer table, and just looking at that, in the 4 records in the customer table, and we've got around 7 rows which we've inserted into the order table. Now that's what we've actually done in our first step, where we got some sample data created, and remember this sample data now as we actually work and try to imagine the logical query processing architecture. Now I will use the next query. Here we have the next query throughout this step for us to understand what's really happening. So I'm just going to pause there while you read that query. The query here returns customers from Madrid that made fewer than 3 orders, including 0 orders, along with their order count. The result is sorted by the count of the orders from the smallest to the largest. The output of this, I will show you the minute I execute this. You will see the output of this query as to how many people we actually land up getting. Now remember, the logic here is we are picking up customers from Madrid that made fewer than 3 orders, including the ones who made no orders at all, along with the counts of how many orders they actually placed, and we are sorting it from the lowest number to the largest number of orders. So we get 2 results here, Fizza and Friendo. One has 0 orders and one actually has 2 orders. That's the result set we basically look at. Both Fizza and Friendo are customers from Madrid who made fewer than 3 orders. Now if you examine the query and try to read it while following the steps which I gave you on my PowerPoint slide, you would be able to imagine the phases in which this query actually went ahead and got itself processed. If this is the first time you're thinking of a query in such terms, it's probably going to be very confusing, and that's why I said take a printout of that order, put that there, and then start thinking about it from the perspective of the first clause was the from clause. So we basically have this as number 1 here, where the from clause was applied. Now this is how you need to think. Now it picked up both these tables. We've got 2 tables here. So the first result was a Cartesian between these 2 tables. And after that, it applied step number 2, where it actually put in this join condition and created a third virtual table. Now this join condition ran on the Cartesian result of customers and orders and gave you the next result. Now I would love to most probably go ahead and split this query and take to you step by step. In fact, I have that query here, but in the interest of the total duration we have for this session, that would take a long time. But otherwise, you can go ahead and just make a Cartesian result here in Imagine Virtual Table 1. Then on that Virtual Table 1, you apply the condition, and then you get Virtual Table 2. Now that was the second step. Now I would like you to go ahead, look at this query, imagine the logical query processing. I want you to get into a habit of doing this more often as you actually work with logical query processing in different phases. Now, so step 1 was the Cartesian result. Step 2 was where it basically applies the on condition, filters the records from the on condition. And step number 4 is where it will add any outer rows, because we've got a full outer join here. So here step number 3 would be it will apply this left outer join and give me a third virtual table. Now I remember telling you guys that the first condition would be to give you a cross join. Then it applies the join condition, the on condition, finds the matching records. Now if you said outer, it has to do something extra. It needs to pick up the data from the left table and add it to this table. So that will give you the third virtual table. So it adds the outer rows. That's step number 3, giving you virtual table number 3. Step number 4 is where you will apply this where condition. So this is step number 4. Sorry, I didn't put a comment here. This is step number 2, and step number 3 is only to do with that left outer join which we are basically looking at. So the first virtual table is a Cartesian result. The second virtual table has the join condition applied where only matching records are available. The third virtual table applies the left outer part of this query. The fourth virtual table would have applied the filter where it only picks up records that are equal to Madrid. The fifth virtual table will do the grouping for you. So now the grouping gets done, and once the table is grouped, you get the fifth virtual table readily available for you to do your next step. In the sixth one, we don't have a cube or a roll-up option in this particular table, so you won't have the sixth one. The seventh one is the having clause. So it will now apply the having clause onto this table, picking up, giving you the actually this would be number 6 here, since we don't have um, a cube or roll-up operator in this query. So this will be step number 6. So step number 6 would apply the having clause and give you the sixth virtual table, and then you would go ahead. Once you've got that applied, it will then go ahead and apply the select clause, picking up only the columns that you actually require. So this would give you the seventh virtual table. Now once the select list is processed and you've got the select list, it will apply any distinct clauses which we don't have in this particular query. And finally, it will apply, we don't have a distinct clause here, so we have nothing to apply there. It will finally apply the eighth step in this particular scenario, where it does the order by clause and returns to you a cursor like we discussed earlier. Now this is the steps of logical query processing. Like I said, it's important to remember this. It's important for you to be able to, we don't have a top clause. If you had a top clause, that would be the last one after the order by clause. So I hope you're able to visualize this query and understand parts of that query which is there. I'm going to switch back to my PowerPoint slide deck here. And we are going to, I've already spoke to you about virtual tables, so you understand virtual tables, you understand the flow of those virtual tables and how they actually work. Let's move on to the order by clause. Now we've spoken about the order by phase, and we've said that in set theory, sets do not have sorted orders. So because of this reason, although every operation returns a table to you. In other words, when we talk about tables, technically we are talking about a set. So sets are being returned at every step, every operation, every phase returns a set. Unfortunately, the order by cannot return a set because sets do not have an order in them. Now, because of this particular aspect, order by is almost always the last operation which runs, because when it runs the order by clause, what it returns is not a set. What it returns is a cursor. Now the frightening thing about it returning a cursor and not a set is you cannot apply further set operations on it once you have a cursor. So all set operations are over. So if you're trying to do a union or a join or any other set operation, you will not be able to do that anymore the minute you basically return a cursor, because no set operations can be applied to a cursor. Now for those of you who are wondering why you cannot have an order by in a view, I think you just most probably understood that concept. You cannot have an order by in a view because you are going to make a query on a view and you want a further set operation to run on it. And if you have had an order by in the view, then it will not return a set, it will return a cursor, thereby preventing you from running any other set operations. And that's the reason why today, because of this very aspect that an order by cannot return a set, so you cannot have further set operations. Today, you cannot have an order by in a view, you cannot have an order by in an inline table valued function, you cannot have an order by in a derived table, and you cannot have an order by in a common table expression. The reasons are very simple and straightforward. You cannot do this because the minute you do this, you cannot apply further set-based operations. So I hope you understand that SQL is purely and completely based on set theory, and most of the operations that we try to optimize are set-based operations on the system. Now that's the concept here which we've actually looked at. We are now going to basically talk about sets. Since you understood sets, you understood logical query processing, let's move on to trying and understanding the differences between sets and cursors. When you work with Transact SQL, okay, you need to most probably, I have a lot of examples for this actually to may help you understand the difference here. But see, when you work with Transact SQL, you try and tell the system what you want to do with the data and how you want it done. Most programming is the other way around. You tell the computer what it should do with an eye on the outcome, almost being a secondary thought. With TSQL, set-based thinking, you will often win by constructing commands that explains what result you want. The query optimizer will then find a good way of arriving at the result. Now, having given you this example, maybe I can think of something relative. Let's talk about sample example here. There's so many examples I could use here. Let's say you had to go to the. I needed some wood to put into my fireplace. Although it's the summer right now in the season, maybe wrong example, but anyway, let's assume you wanted to put some wood in the fireplace, and so I tell you, can you go to the nearby jungle and get some wood for us? Now, guys, what I've told you is the outcome of what I require. And when I've told you this, you will go to the jungle, you'll cut a couple of plants, you might most probably pick up the ones that are already lying around in the jungle, or you might actually go and chop down a tree and bring it and come, or you'll bring a cart, you'll put that on a cart, you will fetch it most probably into the house, or maybe you'll get some people to help you fetch that. In other words, I'm not really telling you what to do. I'm just telling you that I need some wood for my fireplace, and I leave you to basically plan how you go get it, fetch it, and bring me the outcome. So what I do is I tell you what outcome I want. I leave you to basically go about getting me doing the job to get the results. Now that's how a Transact SQL set-based operation and set-based thinking work. So when you're typing a query in Transact SQL and you're trying to run a set-based operation, it's important to visualize and understand you are telling the system what results you want. You're not telling the system what to do. On the other hand, a cursor is a programming construct that prevents the query optimizer from working with the entire set of records that you want to process. So what the cursor does is it queues up the data and then it starts manipulating each row one at a time. The query optimizer then thinks that you are working with only one single data row and will decide how to best satisfy your single row request. Now you can most probably think of this way. Well, I'll go back to the same jungle example. Instead of me telling you I need some firewood for my fireplace, I most probably am going to tell you go to the jungle, pick up a log, and bring it and come for the fireplace. And once you bring in that log and I put it there, I say go back, get another one, and come back. So what I do here is I'm giving you very specific instructions. I'm saying I live on the 11th floor while I'm taking this session today. So I most probably am telling you open the door, go outside my apartment, press the lift button, get into the lift, go downstairs, go to the jungle, pick up a twig that you find fallen there, bring it back, come back into the lift. I give you instructions of what you really need to do. And we do this one at a time. So if I wanted maybe 20 twigs to get my fireplace lighting for the rest of the evening, I most probably will ask you to do this 20 times. So there will be 20 round trips because you will be working on one record at a time. Now, an easy way to demonstrate this, in fact, I love this example which I read somewhere on a blog some time ago, where someone said, let's say, for the women who are there, maybe this is not a good example for you. For the men, let's say your wife told you, can you please wash all those clothes which you have there. Now you can go pick up all those clothes, dump it into a washing machine, get it washed, put it out to dry until I've done the job. Now this is great. Or your wife could tell you, can you wash that shirt? Now once you finish washing that shirt, she can tell you, can you wash the pant too? And once you finish washing the pants, she'll say, okay, can you wash the socks too? You're understanding, a cursor is one operation at a time. And in a cursor, you are specifically telling the system what to do. You're saying, fetch row number 1 and do this to row number 1. So your optimizer plays a role here. Don't forget, ultimately, your optimizer works. But the optimizer is assuming that you are working on only one record at a time. It's no longer a set of records. So this is something that you need to keep in mind. We will work on an example in a demo here where I'll try and give you a simplified version for your understanding of cursors and sets. But to be very honest, although I know this is debatable, I've seen people talk against this, but I'll go straight ahead and say this on record. There are really very few reasons for using cursors nowadays. The programming constructs that are offered from SQL Server 2005 onwards reduced the need even further. And if you're using cursors, you might need to really evaluate whether you're missing something, and you can really actually replace that with set-based operations. So if you have a cursor-based solution and if you want help removing it, okay, you most probably need to sit down and analyze and see what are the things that you're missing maybe in your knowledge of Transact SQL, and try and see how you can refactor that cursor into a set-based operation. Now, having said that, let's move on to our second demonstration of the day. Now, this is a very simplified version of sets versus cursors, but then the intention here is more or less to help you understand. So I'm switching over to my virtual machine right now. Let me close down this last demo that we did, and let me pick up my cursor versus sets Transact SQL command. Now, what we are doing is I'm going to use one of my databases called Credit, which is already available. I'm going to check if there's a table called cursor test in case I've done this demo before. I'll drop it, and then I'm going to create this table called cursor test. Let me just go ahead and create this table called cursor test. Now, the cursor test table has two columns in it, column 1 which is integer and column 2 which is a varchar. Now, I need some data for this, so I'm actually being a little smart here. I'm going to insert into this cursor test table values which I'm going to pick up from my sys columns table, and I'm going to do a cross join on it. This is a simple way of simply getting some sample data into your table. So I'm executing that, and I've got 100 rows which are coming in into this table. Now these are nothing but a row number, and I picked up only the top 100. That's where we got 100. This is a row number, and I'm also picking up here the row itself as a varchar, where I'm picking up a null value and putting it in, and I'm picking this up from a sys columns table, cross join with the sys columns. Now those of you who are keen to just know what's actually inside that after what we've done, let me just put in a star here, select star from cursor test. So let me just show you what we have in that right now. This is what we have: row 1, row 2, row 3. So that was a simple way of simply getting things running. Now I'm looking at a cursor solution here where I'm trying to get the rows and return them to the client. So first I declare a cursor. So I say declare column 1 integer, column 2 varchar. So first I declare two variables. Then I declare a result as a table where I'm going to store all of these values. Then I'm going to declare a cursor called cors and for fast read, and I'm going to now put the data from this table into the cursor. So now the cursor contains these values. Now remember, I had a very simple objective. I simply wanted to select the data. I want to show the rows to the user. But the way I go about this is I declare column 1, column 2 as variables. Then I use those variables inside a table variable called results. Then I declare a cursor which takes all the data from cursor test and puts it into this cursor. And then I now open my cursor. I start a fetch next from the cursor for the two column values, and I keep on while the fetch status is equal to 0. That is, I'm going to continue fetching the records one after the other until all the records in the cursor are completed, inserting it into my table variable called results. Ultimately, I close the cursor, I deallocate the cursor, and then I make a select from my temporary table, my table variable called @results. Now you can see here how we specifically instructed the guy to pick up one table at a time, put it into an area where I could actually pick it up from, and then we basically get the results. Now let me execute this, and you will see I will get the 100 rows again, but I'm using a cursor to fetch each row, put it into a table data type, and then I'm using that selecting from that table data type to see my 100 rows. Now that's a row by row operation using a cursor. Now if you are trying to do this using a set based operation, you are not going to tell the system go ahead and take every row one row at a time and give it to me. You simply tell the system this is the result I want to pick up all the rows from this particular table. Now when I click on execute here, this is a set based operation. I've got 100 rows. I hope I've tried to, I've managed to most probably stress and give you a good perspective on the differences between cursors and sets, and also demote you on using cursors unnecessarily. Use cursors only if you really have something which cannot be done using a set-based operation. Now that's the rule of thumb. Use a cursor only if there's some operation that you need to do that cannot be done using a set-based operation. So that should be your secret mantra which you take away from this particular topic. Okay, let's move on to our next topic, that's temporary tables. And here we're going to discuss the pros and cons of temporary tables. Now, one of the first questions a lot of developers ask is what's the difference between a table variable and a temp table? Now, the most frequent wrong answer which you normally get for that question is that a table variable is stored in the temp DB, while as a temp table, where a temp table is stored in the temp DB, while as a table variable is stored in memory, and that's the wrong answer. What is interesting to know is that both the table variable and the temp tables are both created, and the records for them are both stored in the temp DB. The significant difference, however, is that on a temporary table, you could actually ensure you create indexes if you wanted to. You can go to any column in that temp table, create an index just like any other normal table, which you cannot do on a table variable. That's one difference. The second interesting difference is when you make a where condition on your temp table, and if you have auto update statistics set to true and auto create statistics set to true, SQL Server will not only create but it will also maintain the statistics on those columns which you're using in your where condition or join condition. However, a table variable has no statistics created for its columns. So that's the second difference. Finally, the decision on what do you use. If the number of rows that you're going to be using is a couple of thousand, you can most probably go ahead with the table variable because you can afford no indexing and no statistics. Else, a temp table would be the recommendation. However, a word of caution here on temp tables to especially those of you who are programmers and developers, do not use temp tables because they create a convenience and they create ease of coding. Try and see if you can actually complete your entire programming logic in your stored procedures, especially without temporarily storing the data. Store the data either in a table variable or a temp table only when you have a real need to store the data because the logic calls for the same. Do not do this for ease of programming. Now, I say this because most people do struggle with the performance of temp DB. We have only one temporary space which stores temporary objects and temporary data for all the databases which run on our instance, and usually we are boggled with a lot of issues on the performance of temp DB. Not making unnecessary use of this area, this temporary area, would give you an overall improvement in the temp DB performance. So that's the word of caution to all of you developers that do not use temp tables unnecessarily or table variables unnecessarily. Now, temp tables have two types of creations. You can have a global temp table or a local temp table. A global temp table is created with a double hash next to the table name, and a local temp table is created with a single hash. In terms of their lifespan, both of them would die, both of them would cease to exist once the connection that created them is disconnected. The difference, however, between them, who can see these tables while they exist. Remember, both of them will cease to exist the minute the connection that created them is no longer existing. Those tables would disappear. But while they exist, who could see the tables differentiates between the global and the local. A global temp table can be seen by all users, just like any other table. A local temp table can only be seen by the session that created it. So that's something which you need to keep in mind. Apart from that, there's another problem which is related to temp DB, which is a lot of people go ahead and say create hash table. Now this is great and it works superbly and wonderfully, but maybe this is working super fine for you because the user database from where you're creating this temp table, and your temp DB both have the same collation. You will land up with conflicts in case, let's say somebody installed, when SQL Server is being installed, you usually specify the collation of the instance of SQL Server. Now, whatever collation you've specified for the instance becomes the collation used even for temp DB. Whenever you create a temporary table, it automatically gets created using the collation of the temp DB, not the user database from where you're trying to create it. Now, this could cause conflicts and could cause issues. Of course, there's a new concept in SQL Server 2012 called contained DBs. If you're using a contained DB and you're trying to create a temporary table from a contained DB, it will go ahead and create the temporary table using the collation of the calling database rather than the temp DB. But that is only if you're using contained DBs. So in most cases, you might use your normal databases, and in those cases, I would strongly recommend you specify the collation you want in your create table syntax when you're creating your hash tables. Specify the collation you require so that it does not default to the tempdb collation. And I would recommend this as a best practice, irrelevant to whether your tempdb has the same collation as your user database, because there could be times when you might be migrating this database to another instance, and the other instance has a different collation, and then you will have to go back and recode once again. So you rather do not let your hash tables default to the tempdb collation. You rather specify very clearly when you're creating the table. You can specify the collation which you want the table to be created on. So when you're creating your hash table, specify the collation of the user database for whichever database you are actually creating this table from. Specify that collation in your create hash table syntax. So that would be one of your best practices. Just to show you the conflict, I'll show you a demo now showing you the conflicts of having a different collation in the tempdb and the user database, and what problems this could actually lead to. So switching over now to my virtual machine once again. And what I would do now is I would open up my temp collation problem SQL. What I'm doing now is I'm creating a new database called test, and I'm deliberately creating this using the Finnish Swedish collation. Now I'm just going to also now drill down my system databases here. I'm going to right click on my tempdb. I'm going to go to the properties of my tempdb, and you can see here the tempdb is using the SQL Latin 1 general collation. Now that's the collation of the tempdb, while as this test database that I'm creating right now, I'm creating it using the Finnish Swedish 100 collation. So I'll go ahead and create that test DB. Now once that's created, I'm going to create two tables inside the test DB. One is going to be a table called dbo.foo, which is a normal table, and one is going to be an hash table which will get created in tempdb. But like I told you, since I've not specified the collation when creating this table, it will by default, the hash table will use the collation of the tempdb. So I'll go ahead and create those two tables, and now I'll try to make a query which selects data from the hash table as well as the normal table, and I'm making a join on one of those columns of both those tables. Now you can see here I get an error which says cannot resolve the collation conflict between Finnish collation and SQL Latin collation in the equal to operation. So you can see this join condition gave you a problem because both your tables now are in different collations. Now that's the conflict we spoke about, and the advice was whenever you create hash tables, specify the collation that you want it to be created in, rather than letting it default to whatever tempdb collation is. Maybe you don't have problems today, but you might have problems someday when you're trying to migrate this particular user database to another instance of SQL Server. So I just did a cleanup there, and we've completed that demonstration. I'm switching back to my PowerPoint slides. So that completes our topic on temporary tables, and now we're going to move on to a topic on subqueries. We're going to discuss some aspects of subqueries, and we're going to talk about how they actually work. Now, working with subqueries, a subquery is a select statement nested or embedded with another query. Now, the nested query, which is the subquery, is the inner query. And the query that contains the nested query is the outer query. So naturally you have one query, and inside that you have another query. So you have an inner query and you actually have an outer query. The inner query is called the nested query. It's the query that's nested inside the outer query. Now the purpose of why you might be using a subquery is you want to return results to the outer query. The form of the results will determine whether the subquery is a scalar subquery or a multi-valued subquery. Scalar subqueries, just like scalar functions, returns a single row. Outer queries need to be written to process a single result. Multi-valued subqueries return a result much like a single column table. Outer queries need to be written to handle multiple possible results from the inner query. In addition to the choices between scalar and multi-valued subqueries, you may choose to write subqueries that are self-contained or subqueries that are correlated with the outer query. Now, self-contained subqueries can be written as standalone queries with no dependencies on the outer query. A self-contained subquery is processed once when the outer query runs, and it passes its results to the outer query. Now, this is self-contained. The correlated subquery references one or more columns from the outer query and therefore depends on the outer query. Correlated subqueries cannot be run separately from the outer query. So, and they are usually performance intensive. So your subqueries can be scalar, multi-valued, or they can also be table valued. Now that's all about subqueries that you have. Now, when will you use which type of subquery? Will it be self-contained? Will it be correlated? All depends on the logic which your application is demanding and what output you're actually looking for. Now, writing scalar subqueries. A scalar subquery is an inner select statement within an outer query written to return a single value. Scalar subqueries may be used anywhere in an outer transact SQL statement where a single valued expression is permitted, such as in a select clause or a where clause or a having clause or even a from clause. To write a scalar subquery, you need to denote a query as a subquery. You need to enclose it in parentheses like you can see on the example in the slide. Multiple levels of subqueries are supported in SQL Server. When I talk about multiple levels, one inner query can be within one outer query, and you can go on nesting it this way. But you can go up to 32 levels because that's the kind of support. My recommendation is don't. The system would support it, but you would be so confused by the time you finish that query, you would not know what's being returned. But yes, the system does support up to 32 levels of nesting of subqueries. If the subquery returns an empty set, the result of the subquery is converted and returned as a null. So you need to remember this. You need to ensure your outer query can gracefully handle a null in addition to any other expected results. For example, order by is equal to null. Is this handleable by your outer query is something. In case your inner query in this example that you're seeing returns a null value, because if no records are returned, it will return a null value. Now, can your outer query gracefully handle that value apart from other values is something which you'll need to keep in mind while you're actually coding a subquery. So you got an example there which you're actually looking at right now, and which you're what we're trying to do right now is we're trying to pick up the max order ID and we're trying to pass that as a value to the inner query, to the outer query, in order to return the results of that query. Now you can also write multi-valued subqueries. Now what you're looking at here is a multi-valued subquery. Now the multi-valued subquery, as its name suggests, multiple valued may be returned and more than one results in the form of a single column set. A multi-valued subquery is well suited to return result sets using the in parameter, like you can see in the example that we have here. The in predicate is more suitable. So you say customer ID in, and then you put in your multi-valued subquery so that it's able to support the multiple values which are actually returned from the inner query to the outer query. We can also write correlated subqueries. Now, correlated subqueries are things which you need to most probably be careful of. This is where the confusion starts because the visualization becomes difficult. Like any self-contained subqueries, correlated subqueries are select statements nested within an outer query. So that's not different at all. They may also be written as scalar or as multi-valued subqueries. And they're typically used to pass a value from the outer query to the inner query to be used as a parameter there. However, unlike self-contained subqueries, correlated subqueries depend on the outer query to pass values into the subquery as a parameter. This leads to some very special considerations when planning their use. Correlated subqueries cannot be executed separately from the outer query. This complicates testing and debugging, of course. Unlike self-contained subqueries, which are processed once, correlated subqueries will run multiple times. Logically, the outer query runs first, and for each row returned by the outer query, the inner query is processed. Now, for example, which you're looking at right now on the board, it uses a correlated subquery to return the orders with the latest order date for each employee. You can notice the correlation here and the dependency that we are actually looking at here. So we are saying, give us the max order date from the sales.orders table. Now that's where we are trying to pick it up from as O2, where the employee ID being returned from the outer query is equal to the employee ID being from the inner query. So you can see here we've got 01 and 02. 01 is your outer query, 02 is your inner query. Both are the same tables. Now you notice the inner query cannot run unless you first throw up a row from the outer query. So for every row being returned from the outer query, the inner query would run once and throw up that particular record. So that's the correlated subquery for you. This could also be nested multiple times. Okay, if you examine this query in a trace, the role of each clause would be become visible for you. For example, the select order ID, employee ID, order date columns are returned by the outer query. The from sales.order as O1 sources the tables for the outer query, not the alias. Where order date is equal to, this predicate is used to evaluate the outer rows against the result of the inner rows. And the selects max order date columns returned by the inner query aggregates the functions, returns a scalar value. The from sales.orders as O2 source table for the inner queries sources the table for the inner query. Note the alias. It's called O2 or 02. Where 02.employee is equal to 01.employee ID. This is where the correlation takes effect, where you're trying to pick up a value from the outer query and match it with the value from the inner query. And then you actually have an order by which sorts the final results of the entire query after it is actually completed. So writing correlated subqueries could actually be tiresome. It could need you to visualize your outputs and what actually is your output. For example, you can look at the inner orders.cust_id is equal to outer orders.cust_id. I've tried to put that there so that you understand the inner and the outer tables being joined and the correlation that you actually see there. You need to write the outer query to accept the appropriate return results from the inner query. If the inner query will be scalar, you can use equality and comparisons such as equal to, lesser than, greater than, and not equal to, and so on in the where clause. If the inner query may return multiple values, then you need to use an in predicate, and you need to also again plan to handle null values here. You need to identify the column from the outer query that will be passed to the correlated subquery. Declare an alias for the table, that is the source of the column in the outer query. You need to also identify the column from the inner table that will be compared to the column from the outer table. Create an alias for the source table as you did for the outer query. You need to write the inner query to retrieve values from its source based on an input value from the outer query. For example, you can use the outer column in the where clause of the inner query. The correlation between the inner and the outer queries occurs when the outer value is passed to the inner query for comparisons. It's this correlation that gives the subquery its name as a correlated subquery. So that's about our correlated subqueries and how you could actually work with it. You can execute these sample codes that you're actually seeing right now on the slides. So I'm not taking you into a demo there since I've shown you those codes itself. I'm now going to move on to our next part where we're going to discuss some new analytical ranking functions. There's lots of functions which we could have discussed, quite a few of them which you most probably already are aware of, like the aggregations and so on. So based on the duration that we have in this session, I'm going to stick to some of the new analytical functions that's available. there are 8 new analytical functions that have been added to TSQL. All of them work in conjunction with an ordered window defined with an associated order by clause that can be optionally partitioned using a partition by clause and framed with a between clause. So this is what we call the windowing functions, where instead of trying to work on a complete result set, you can partition your results into windows and you can work on one window at a time. So this is something which SQL Server has been enhancing from version to version, and a lot of functions have been added to support the windowing functions. So today when we talk about these new analytical functions, you need to remember they have to be associated with an order by. They could be partitioned by a partition by, and they could be framed with a between clause. The new functions that we'll be discussing today is the first value, the last value, the lag, the lead, the percent rank, the cumdist, the percentile count, and the percentile disk. Now we will look at some examples here and we'll see how to actually work with these functions. That's usually going to be the best way of understanding them. Different queries are going to be available, so I'm going to switch over and show you a demo of each of these functions very quickly. So I'm going to switch over to my management studio here and I'm going to double click on the analytical functions. Now I'm going to declare a table called at the rate of orders. I'm going to say as table. I'm going to insert some values inside it, and here I'm going to use a select command. Let me just minimize this, make this a little larger so that you can see this whole query. I'm going to hide that. There you go. So now the entire query is visible to you. So this is a table which has order date, product ID, and quantity. So this is a table variable I'm creating for this example. So order date, product ID, quantity, 3 columns. These are the values which I'm inserting into this these columns. And here you can see I'm using the first value of the order date and the last value of the order date. So this is the lowest and the highest. I'm partitioning it by the product ID. I'm ordering it by the quantity. And I'm saying rows between unbounded preceding and unbounded following. I'm also using the lag here on the previous I'm calling the lag order date 1 and product next on lead order date 1. Here also we are partitioning it by the product ID and the order date, and overall we are sorting it. Now if you look at this particular query here, we've got the same product which appears multiple times. You see 123 here is twice. We can also see that we do have 101, 101, 101. Now let me just show you these results, and you will be able to most probably interpret what your query actually did. Now the order date is here, the product ID is here, the quantity is here, the lowest on. Now this was when you actually put in your function called first value. So this is the lowest order date. Now you can see in this particular case it was the same date for this particular order. This is the highest order date for this particular product. So this was the first order placed for this product ID was on this date, and the last order placed was on this particular date. In case there was a previous order for this, I'm looking at the previous order, but in this case there was no previous order which we actually add for this, so I'm don't have a previous order. And we've got the next order on, which is going to tell us which is the next order on, which is there only for a couple of rows, because I'm throwing up every row. You notice there are 7 rows here, and that's 1 2 3 4 5 6 7. Now this was at this row level, this was the lowest and highest order date. There's no previous and there's no next for this particular product. For 123, product ID 123, you notice this is the lowest order, this is the highest order which we have, and the next order date was for 123 was 725. So that's why I've got the next order date right here available. So we've seen 4 functions there, one shot in that particular query. You've seen the first value, the last value, the lag, and the lead. The lag here in this particular case 101, you can see this was the previous order which was on this date. So you can see we've got the lag value as well as a lead value, because there's one more record here for 101. So that's pretty interesting how you can actually use these analytical functions and throw up most probably queries which you never anticipated you can do before much easily. Now the second example I'm going to show you here is we're going to use the percent rank, the cumdist, the percentile disk, and the percentile count functions. So I'm creating a table here which has year, quarter, and amount. I'm inserting a couple of records here, to be precise 8 records we are inserting into this table. and we are now going to make a select here where we are going to use the rank, we are going to use the percentile rank, and we are also going to basically use the cumdist. I execute this now, and here you can see we've got those analytical values throwing up for us, the where we've got the PR, the percent rank. We don't have it for the first record. This is rank 1. Both of these are rank 2 because the amounts are tied. We've got this at rank 4. We've got this at rank 5. We've also picked up the percent rank for the order amount, and we've also picked the cumulative distribution for the order amount. So that's another 3 functions which I've covered for you there, and I'm going to now show you the percentile lookup. So I'll just execute both of this together because we need that table variable here. So there you go. So you've already understood the rank functions which you've seen here. I'm now taking you through another set of functions which you have here, where I'm putting in the percentile disk and the cum disk and the percentile rank together. Let's execute this now to give you both the result sets. Okay, I'm just going to try and first show you this query so that you're able to, you can freeze the screen here in case you wanted to take down this query or understand it. But what we are picking up here is the year, quarter, month, then we're picking up the rank, we are picking up the percentile rank, we are picking up the CD, we are picking up the percentile disk, and we are giving it a 0.5, 0.6, 0.5, 0.6 here. So we are trying to order it by the year inside this. Now let's have a look at the results that we've actually got there. Now here you can see we've got the PD5, the PD6, the PC5, and the PC6. So each of them actually throwing up right now, giving us the percentile values of them. So these are new analytical functions, could become pretty useful instead of you trying to do a lot of coding in order to basically get them to happen or work with. So that's our topic on what we have in terms of some of the new analytical functions that's available with SQL Server 2012. Of course, they have to be used with the partition and the order by clause, most of those functions which you've seen out there. Now we're moving on to our next topic, which is queries and join strategies. And I'm going to do this completely with a demonstration where we'll try and understand what are the various join strategies that's available. We'll also look at in this the impact of indexes and how indexes actually impact the kind of join strategies that really get implemented on your system. So I'm switching straight back to my window, my management studio here, and let me actually start by looking at a normal query where we will try and understand firstly how an index can impact a query. I'm going to use a sample database here called credit. I've got a stored procedure created here to clean up this table in case there were any indexes on it. So let me execute that, where all the indexes and the statistics get cleaned up. I'm creating 4 indexes, all non-clustered, one of them a unique non-clustered, on 4 different columns in this table called charge. I'm creating a unique non-clustered on charge number, a non-clustered on member number, another non-clustered on provider number, and another non-clustered on category number. So I go ahead and create those 4 non-clustered indexes. And before we really execute some queries to see how these things work, I'm going to show you some analysis of the data that we actually have in these 4 columns that we've indexed. You will notice we have 1 lakh rows in this table actually. The minimum value that we have in the category is 1 and the maximum is 10. Now this actually tells you that there's a lot of duplicates in this particular column called the category number, because if you have 1 lakh rows and you have to use only numbers 1 to 10 in that 1 lakh rows, that means there's going to be plenty of duplicates in the category number column. We have the charge number column, which is a unique non-clustered index, which means you have all unique values. Your minimum is 1, maximum is 1 lakh. Member number has some duplicates. Minimum is 41, maximum is 10,000. Provider number also has plenty of duplicates because minimum is 18, maximum is 500. So these are the range of values which need to get distributed across a lakh. So what you understood from this query is a bit of density information. You understood what kind of density is there in this data. Now I'm going to run one query. Let me go to the query and say include actual execution plan. And let me execute this query for you and show you the execution plan. Now this did a table scan, although if you're looking at this query clearly, we actually have the where condition being made on the charge number column. In spite of us having the where condition on the charge number column, which has a unique non-clustered index, the optimizer decided not to use the index because he found your where condition not selective enough. You actually asked to pick up all the records right now here. You said 1 to 1 lakh, and he says, funny, I don't want to actually use your index because you're picking up all the records. So what I'm going to do is I'm going to bring this down to just 1 to 1000. So I'm picking up only 1000 of the 1 lakh records. And for those of you who might be surprised here, it's still using a table scan. Now, if you understand this table structure, this is a table which is on a heap, and we've got a non-clustered index on charge number. So let's look at it this way. Now, this guy could most probably go to around 2 or 3 index pages maximum, where he's going to find the charge numbers 1 to 1000, maybe on a max of, let's say, 3 or 4 index leaf pages, non-clustered. And what he finds there is charge number 1 and then the address, the row number, page number, where he needs to go to pick up the remaining records from the table, the remaining columns, because your query here says select star, which means you want all the columns. So he needs the other columns. Your non-clustered index only has the charge number and a pointer. Now, because of this, for every pointer, he needs to hit one data page. And here, you're returning 1000 rows, which means he needs to hit 1000 data pages. At this time, it's good for us to run set statistics IO on. Now let me just show you this. I execute this here again, and in the messages you can see, doing a table scan, we read 596 pages in order to give you the 1000 rows. The table scan, the total pages for this table is 596. You read all the pages in order to return 1000 rows. But if you had to use an index for this, you would be touching over 1000 pages, because for 1000 rows you'll have to hit 1000 pages, because every time you see an address, row number, page number, you go hit get the record. Again, you get another row number, page number. You need to do this for every pointer that is being given to you by a non-clustered index, and that's the reason why this system landed up using a table scan. So the system was pretty right, because your IO now if I change this query where I say I want only the charge number and then I execute, you will see the execution plan now uses the index, because he does not need any more data, because you only asked him for the charge number. The charge number is very much in the index, so he does not need to go anywhere to assess data. So he goes only to the index, and you will notice he reads just 5 pages from the index in order to give you the 1000 rows that were returned, but he's giving you only charge number. Now the reason why he uses a table scan for anything else, because the minute you add another column, this other column that we've added is not in the index, and since it's not in the index, you will now need to actually go to each data page. So you can most probably visualize the index. Charge number 1, it says go to this page, go to this row, and pick up the rest of the records, the rest of the values, columns. Charge number 2, this is the page number, this is the row number, go there and fetch it. Charge number 3, this is the page number, this is the row number. Now you're understanding, we have 1000 such pointers, which means he needs to hit 1000 pages. And that's the reason why he would touch 1005 pages if you forced him to use the index in this scenario. However, if I change this to 100, and I look at the execution plan, and amazing, he uses my index. He does an index seek here, so most probably this would touch maybe around 2 or 3 index pages, and he picks up 100 pointers, because 100 rows are being returned. He uses a nested loop here, does a row ID lookup on the heap for the 100 rows, and gives me the 100 results. So the page IO here would be maybe around 3 index pages, and 100 data pages had to be it. So if you look at the messages here, you can see the logical reads are 102, so that's 2 index pages and 100 data pages. Fair enough, you used your index. So you can see here how the IO determines the kind of index that gets used, or the kind of plan that actually gets built. Now, having said this, let's look at how this influences your join strategies. Now, there are 3 join strategies that are available. I'm going to open up one of them. You have a nested loop strategy, you have a merge strategy, and you have a hash strategy. Now, a nested loop strategy is when the two join columns. So you have two columns which are there, and any joins will have two columns. Now in the two join columns, if one of the columns, that is the outer table, that is the table which has the lower number of values, which is the outer table, and the inner table, if the inner table has an index on it. Now the meaning of having an index on it means the column values are sorted. So you have one set of sorted values and one not sorted values. In this case, the system will use a loop. Because the inner table is sorted, he does not have to go to the last row there. So he'll pick up one value from the outer table and match it with the values in the inner table until he finds a match. Now this is a loop strategy. Now guys, a lot of people believe, okay, in fact, I've always seen this expression. I always believe it was a dumb recommendation. Index your foreign key columns because it will improve. They could be used in joins. Now guys, just creating an index is not important. You just seen in the last demo, you might have an index, but the index may not get used. If you do not use the index, then you are not getting sorted values. And if you're not getting sorted values, you will not land up using the strategy that you actually want. A loop join strategy works if your inner table, that is your larger table, is sorted and your outer table is not. Having an index, that means your primary key and foreign key, as simple as that. So your foreign key column having an index on it could most probably enforce a loop join, but guys, only if the index gets used. If your query is as bad as our query that you've seen in our last demo, where the charge table had a unique non-clustered index, but the index was not getting used, in such a scenario, it's as simple as this. You're not having sorted values. So the join strategy will not be what you're looking for. Anyway, let's look at this demo here. So I'm going to use two tables naturally, the member table and the charge table. On the member table, I'm creating an index on the last name and first name. That's a composite index. And I'm creating another non-cluster on the member number from the charge table. So you notice now member number is indexed, last name and first name is indexed, but member number from the member table is not indexed. Member is the master table. Charge is the detail table. I'm indexing member number, which is the join column, in the detail table, not in the master table. So I'll go ahead and execute that, create those indexes. And once those indexes are created, I have a query here in which I'm trying to enforce. Let me include the actual execution plan here, and now you notice here the join condition is on member.member number is equal to charge.member number. If you remember, we've got an index on charge.member number. We don't have an index on member.member number. This will ensure when I execute this now, if you look at the execution plan, you will notice I've got the index seek on the member name, and then I pick up those values. So this is the master table, the outer table, and then I've got the charge here, which is the inner table, which is now I'm using the index here on the charge table for member number, charge.member number. Since I'm using the index, these values are sorted. So I've got one set of records, that's the master table, which is not sorted, and I've got the detail table, which is sorted because I'm using that index, and the join strategy which he uses is the nested loop inner join strategy. It's as simple as that, and as comfortable as that. Now just to show you the other aspect here is, now the reason why this index is getting used, because you have a last name and a first name which is here, and you're filtering it and picking up only certain records. Let's say I execute the same query without the where condition on the member last name and first name, and I execute this now. In your execution plan, you will see two table scans happening and a hash match join. Now in hash matches, when you need to join two tables which are not sorted. So two columns here are being joined, both these are not sorted. Now I can hear the objection. You're telling me charge.member number has an index, it is sorted. But guys, for us to get that sorted value, the optimizer must choose to use the index. But because your query was not selective enough, the optimizer decided to let go of your index and not use it. Now since it's not using your index, you don't have sorted values, and since you don't have sorted values, it's using the hash match strategy. Now the loop strategy, I think you visualized, it picks up one value from the outer table, which is the smaller table, and goes to the sorted inner table and matches it with it and returns the matching records. Now in a hash match, what he does is he picks up the table from what is called the probe input and the probe output. So he picks up the tables, the values from the probe input, creates an hash key for every value which is here, creates an hash bucket for the larger table, and puts in all matching records into that hash bucket. So here the matching is done by the hash key. If the hash key matches, all the records in the hash bucket are returned. So he does not do a row by row matching for everything. So all he does is he groups up. Maybe this is the wrong terminology, but this is a good way to understand it. He takes the large table, groups up all values with the similar member number, which becomes the hash key. Member number becomes the hash key. Groups all the records that have the same member number and puts it into a bucket in memory, which is called an hash bucket. He takes the member number, creates an hash key out of it, and gives the bucket the hash key as its ID. He does this now for every member number in the larger table. So you have multiple hash buckets having multiple records which have the same member number. Now he goes to the master table, he picks up the member number, maps it with the hash key of the bucket. If the members numbers match, the entire bucket is returned because the bucket now contains all the rows that have the same member number. That's how a hash join actually works. Now for a merge join to work, I think you most probably have figured it out already, we need to have both the columns sorted. Again, just indexing them will not mean that they will be sorted. Your queries need to be good enough to use them. So I'm just now cleaning up the member table and the charge table, and what I'm doing right now is I'm creating two indexes. You notice I've got indexes being created on both the member numbers, member number from the member table and member number from the charge table. Now all I need to do is build a healthy query which ultimately lands up using both those indexes so that I get those sorted values. So I'm putting in, since the last name is here, I'm putting in select where member number and last name. I'm going to hope that my optimizer finds those indexes useful. Sorry, I forgot to include the actual execution plan here. Let's execute again. So I'll check the execution plan here, and you can see I'm using the merge join. Those indexes were found useful which I had on member number, and he does a merge. The merge join is the fastest possible join you could ever use, because in the merge join it does not do looping, it does not have to create the buckets because both records are sorted. It simply merges the records together. So the sorting, and it does far lesser work than both the hash and the loop. But unfortunately the prerequisite is both columns that you're using in the join need to be sorted, which cannot always be the case. So the other strategies are equally important. So that's about join strategies and how indexes influence join strategies. That's what we tried to look at here. And the last topic that we will be doing for today is about pivoting data. Now, pivoting data is about rotating data from rows-based orientation to a column-based orientation, and the distinct values from a single column could get projected across as headings for other columns. Now you can see here what the pivoted data actually, which you're pivoting, would actually look like. Now for this to happen, however, you need to have these values in advance: 2006, 2007, 2008. You need to know these values because they become your column names. You'll need to hard code them in your query. I would recommend you look up the syntax for that. I'm going to show you one sample here of the same. You can see the elements of a pivot here. This is the table we are looking at actually, where you got all the categories, the quantity sold, and the year in which it was sold. This is the table on which I'm going to build this query. So I'm selecting the category, which is the grouping column. I'm typing in values which become my new column. So now this is the problem with pivots. You'll need to know these values in advance. 2006, 2007, 2008. I know they exist. I'm going to say from, and here I'm going to say select category, quantity, and the order year from sales.category year as D. And I'm going to say pivot these values now which are coming, sum the quantity for the order year for each year. In 2006, 2007, and 2008, you can see this should match. Okay, so we are spreading this out as pivot. Now it's as simple and easy as this to pivot, and it's almost exactly the opposite of that in case you want to actually unpivot. Now looking at the elements of a pivot here, okay, we've got the results here from this particular query, and you can see what happened here was this became the column names. We got the grouping here by each category. we got the quantities. So this query would have thrown up multiple, it's not grouped as yet. When you say pivot, some quantity for order year, this is where the pivot actually takes place, where you have 2006, 2007, 2008, and it gets grouped by the category which you're actually looking at there. So pretty interesting query. I use this very often actually, especially in reporting. Lots of times you would like to most probably pivot because normalization sometimes messes with the way you would like to view data. So normalized data may not be viewable, so pivot could actually become a pretty interesting function for you to use. You can also do the exact opposite. You can unpivot. For example, this is exactly the opposite of what we've seen. Here we've got the categories, we've got each year as a column, and now we would like to actually convert them into category, quantity, and order year. Now, this is done where you select the category, quantity, order year. From category, you say unpivot quantity for order year in the years you want. So this is a far simpler and straightforward query than the pivoting, and that would give you actually the results you wanted. Now this covers all our topics that we really want to cover in this session. I thank you all for spending the time. Hope this was quality learning. Hope you got value from the time you've spent. This is Christopher Richard from G7CR Technologies signing off with thank you very much for attending this session.